Welcome. The subject of my dev forum is going to be on Valgrind and other tools to help you debugging memory corruption problems. First, just a little bit of background. My name is Topolsky. I work at the SIB as a software developer. I have quite some experience in C, C++. Actually, I have been bitten by the bug when I was still a teenager. And during my previous job at the SIB, I was helping with the software packaging and deployment on the Vitality cluster, which means that I have seen my fair share of problematic software with memory corruption and so on. Currently, I work on the vpipe SIB resource, which is NGS virus pipeline, which specializes on quasi-species. And among other role that I have on this resource is also do the maintenance on software. So one of the example I'm going to show is one of the components of this pipeline. Now, let's speak a little bit about the type of memory corruption bugs that you can see. You can have things like yeah. You can have things like memory leaks, which are situations when suddenly your program starts to use more and more memory and never free it. You can have situations where your program starts reading from memory where it shouldn't be reading at all. For example, parts of the memory which aren't initialized yet, so which don't contain the default value that you want, but just whatever stupid noise was there. And at the end, you end up with some really weird noise in your data. Other possibility of memory corruption, situation where you start writing on memory where you shouldn't. For example, when you start reaching beyond the bounds of the memory that you have allocated, or where you have problems because you use the wrong type of pointer operation, so you're casting to the wrong type and therefore accessing it the wrong way. Or also situation where you start, or you continue, writing to the memory long after the point where you have it normally given back to the system. In this case, depending on the exact memory layout at the moment, you're either going to have seg faults and other critical errors, or again, your results are going to have some weird noise in them. So when is the moment when you need to think about memory corruption? Like I said, if you have seg faults, you'll be needing to think about memory corruption leading to that. Or if the data that you're getting out of your software is completely corrupted, for example, the text is turning into pieces of whatever, or if the numbers absolutely don't make sense. For example, if you have a probability value, which instead of being between 1 and 0 is actually above 10,000. Also, this special class of bugs known as Heisenbugs, which are situations which you actually cannot replicate. Example, the repairman doesn't see the problem which stopped the coffee machine for everybody in the office. Some of them may actually be due to memory problems, mostly if you manage to have problems with your memory allocator, or in some really weird situation of out of memory bounds. So it might be good to try to see if your software is actually working as it should, or if it's starting to write somewhere where it should. But also Heisenbugs can be caused by completely different situations, like race condition during multi-threaded execution, in which case, well, you'd need different kind of tools to illustrate the bug. Valgrind is a tool which is a little bit old, but has seen a lot of deployments everywhere. So it's a proven one, which is well known. You can easily find documentation about it everywhere on the internet. This tool works by having a virtual machine. The binary you're trying to execute is going to be converted into some intermediate representation for this VM. Then you have different tools which will add instrumentation to help you check whatever you want to check. And then the thing is jittered and executed. Because it's a virtual machine, it's going to be extremely slow. It also has access to a debugger, so you can debug with GDB if you want, and also you get all the extensive information about which line of code caused your problem. The main tool with which I'm going to starting is the memcheck tool. That's the tool which is used to debug memory problems with Valgrind. It keeps track of the memory. It's constantly, for every position in the memory, keep information if the content of the memory is valid. For example, if it was initialized or if it currently contains garbage. And also if it's addressable, if actually this memory was currently allocated by the software, or if it's just memory outside the bound of everything. You can use it to find problems with initialized memory. So you're trying to read something where you didn't put any value in advance. So sometimes you get weird values instead. It can help in situation where you're still trying to access memory, although you're supposed to have him be already given to the system. And it can help you also detect when you're reading and writing beyond the boundary of what you've asked the system. Also, it helps detect memory leaks because it tracks every single location. It can tell you if some part of your program is constantly allocating but never giving the memory back. In addition to Valgrind, just to be a little bit more complete, there are also other tools which exist. These tools, for example, are the sanitizer. Sanitizer are type of tools which actually instrument directly from within the compiler. They're both available for Linux, for GCC, and for Linux and Mac OS X in LLVM. They are much faster because they don't go through a VM, like explained before for Valgrind, but they do a little bit less tracking because it's not actually intercepting every single memory access and keeping attributes like valid and addressable, like we mentioned before. So there are a few situations where it won't be able to find the error, or it's going only to tell you an error, but we'll be having difficulties to track back where the error came from. On the other hand, like I said, it's much faster, so it's always useful to give it a try. The sanitizer I'm going to demonstrate shortly is the address sanitizer. It's specifically done for memory corruption bugs, like we said, for use after free and for buffer overflows. There are other sanitizers which exist, which might be useful for you. There also exists the undefined sanitizer, which is a sanitizer which will be trying to check for situations which your software runs into, which actually are not defined into the C standard. One of the examples is overflowing value. The physical implementation of your CPU makes it that there's a maximum value it can take, and if you increment it, it's going to loop back into the negative. This type of error got quite some public exposure due to having been the cause of a new generation of Ariane blowing up, because the value were still mapped to 16-bit registers from the older generation of Ariane, and the value eventually rolling back. Another type of situation that an undefined sanitizer can help you track is finding invalid parameters to function. For example, the memcopy function of C should never receive a null, or should never receive overlapping source and destination. Because if you want to copy these 6 starting at this position, depending on the direction in which it's copying, either you're going to get the exact correct thing that you have been expecting, so all the 6 numbers map from here to here, or if the software is copying the other way around, it's going to copy the first 3 correctly in position, but then because it's still proceeding from left to right, it's going to see 3, 4, 5, is going to see the 0, 1, 2 that it already copied before, and you're going to have your value duplicated. It might also happen that by pure luck, your software happens to be working on your computer because your computer happens to be using the correct way that makes your software work, but because you're calling the functions not in the way they're supposed to be, if you move from one machine to another which has a different implementation, that's going to make you some problems. A third one that I'm just mentioning because I'm not having much experience with that one is the thread sanitizer. The thread sanitizer is mostly used to find racing condition in multi-threading, where some threads try to access data before it has been correctly released by the other. So now I'm going to try to show you a couple of first small trivial tests. I'm going to show some very trivial situation. This is typically something which shouldn't be allowed. You're allocating memory, you're then deleting that memory, and then once it has been released, you're trying to access it nonetheless. So first, I'm going to demonstrate how it works with the sanitizer inside the compiler. So the command that you need to run is run the compiler as usual. You'll need to have some debugging enabled so you can get some meaningful information, and you activate the sanitizer that you want. In the current example, I'm turning down the optimization to avoid the bug actually being optimized out, because it's a really trivial example. Now, if I execute it, you see that the sanitizer has correctly detected this class of problems. It's telling me where the error is arriving. It's telling me where the thing was allocated and when it was freed before. I'm getting all the information I need here, here, and here, so I can debug. Also, it's also displaying me the current content of the memory. As you can see, the memory has been overwritten with some invalid value, and that's the one that the instrumentation inside the compiler for the sanitizer is using to detect the problem. Now, I'm going also to compile it simply without the sanitizer, and I'm going to run Valgrind on it. Again, Valgrind is working. It tells me a little bit about where the read problem is happening, or the memory got freed, and where the memory got allocated before. Again, I could have had all the information I would be needing for. You can also try the same with a different example. This one allocates memory, but try to access it above. So first, I'm going to compile it with the sanitizer, run it. As you can see, again, you get the information where the error happens, and it tells you that this happens not far away from that memory location. So there might be some chances that the thing that you were trying to access had been this one, and you simply didn't get enough memory allocated. Again, it gives you enough information to be able to debug. And again, here's the current representation of the memory. You see that the buffer itself was correctly allocated and cleared with zeros. And then you see that currently we were accessing outside of the region, in a region which was specially marked by the sanitizer with an invalid value. Again, I'm going this time to compile it without the sanitizer, just with debugging. And I'm going to run Valgrind on it. And again, you can see that we are currently having the problem where it's happening, the region where the memory was allocated, which is most likely the one that you were aiming for, and you get everything you need to be able to debug. Now I'm going to talk a little bit about a real-world problem that we got with the pipe. Sorry. I want the screen. Wow. Yeah, I want the screen, which is you. Yeah. So sometime after I arrived, we got this weird result being displayed by Shura. The thing is, this column is supposed to be a probability. It's supposed to be mapping between 0 and 1, not minus several million. When you see this type of weird values, and especially the fact that it wasn't correctly, and that it's replicated after several lines, might give you an indication that the value wasn't correctly initialized. So let's see the actual stuff. First, I'm going to go on my software, and if I run the software with Valgrind, it's already getting interested even at this situation, because if I scroll back, I see that very often there are some initialized value all being called by this line of my program that can give me an indication where the problem is occurring. If I go to this line in the source, here it is, sorry, there, I see that this value indeed isn't initialized. I can try to look where it is called. And normally here, you see that it's being assigned, but it's only being assigned if these conditions are correctly held. If it's not held, this function, which is automatically called in the inner loop, will exit without assigning it, and whatever random value happened to be into this structure here is going, where it is, sorry, here is going to be the one which is going to be output to the screen. So to resolve that, we need to create a function which will automatically initialize some values before the loop, and which is then going to be called in the inner loop before gathering the data. So with that, I can now go to the version that I showed you before. And now if I execute it, all the problems have been gone. We don't have any corruption announced anymore in Valgrind. And, sorry. And that eventually will fix the output to something which at least makes more or less sense. Another example that sadly I don't have the actual data access to due to medical restrictions, patient data. I'm only going to show you the debugging happening. We had a very weird situation with my colleague here, Mustafa, where some software ran correctly from one directory, but didn't run correctly from the other. If it's only sometimes seg faults, one of the reasons might be memory corruption. In this case, it happened that depending on how it was allocating its buffer, it managed to either land everything on the same page and nothing was happening, or there was some corruptions which only happened every now and then. The fact that we were able to use Valgrind enabled us to pinpoint the situation to here. To optimize, the algorithm was setting some memory aside, but when reading, happened to be reading more than needed. So depending on the mapping on the memory, if all the buffer happens to be located at the beginning of the page, there happen to be just enough allocated pages after the end of the buffer, so any out-of-bound memory didn't trigger the bug. The only way to detect the bug was actually to run it into Valgrind, which would detect the access to a memory which wasn't actually allocated. So even if there's no problem at the page level from the kernel, tools like Valgrind or Sanitizer will be able to find you problems at the malloc level in your application. And we are able to correctly ask the correct buffer in our testing, then it managed to work. So now for the second half. Oops, sorry for the typo. So a little bit about the optimization that went into Shora, most likely the Diri sampler step. For those of you who were present at the Ascona workshop, I actually presented the optimizations on one of our posters. For the small test set I was using to optimize, the run managed to go from 18 minutes down to 8 minutes for the whole giant data set that we use to stress test our systems. The whole processing time also managed to get faster. How did we do? First, how we did not do. Do not micro-optimize. Do not first jump to trying to hack everything. First, things which were done much before my arrival are big obvious things like thinking about an appropriate algorithm in terms of big O notations. That was done by all the past PhDs which were working on this before me, so that we actually have something which is more or less efficient. Also, for key point of the algorithms, the one which are very often called, you can take a little bit of time to find ways to express it in a much faster situation. Here, to check difference between sequences of DNA in the sampler, our current PhD managed to optimize using a simple hardware instruction which computes the difference in bits in just one instruction. So only once you're sure that you've been done the good large-scale things like having correct architecture and having the most important steps actually done correctly, then you can try to look a little bit and think, are there other places where you can optimize? So once the big picture has been done, only now you can remove the small craft left everywhere. No, the question is, where it is actually the most worthy to do? For that, we're going to use a call graph to determine which function has the most time spent inside or is the most often called. And actually, as a background story, the fact that I decided to optimize this is because first, as a sanity check, I decided to use Valgrind in the previous memcheck mode I showed before, just to be sure that it's not corrupting its memory silently and just not displaying bugs in our situation. And while running this, I found that it's calling malloc for hundreds of millions of times. So, well, let's try to find out where these mallocs are getting called. So to do that, Valgrind has different other tools. One of them is callgrind. Callgrind, you can call with a special command to ask that tool instead of the default memcheck, and it will bring build a call graph of everything which has been happening inside your software. And it uses a nice interface for that. You can use the KDA software called KCacheGrind, which will give you a very nice interface to visualize your data. As a side note, I must also mention other tools which are commonly used for these kind of things. For example, the GNU profiler. Most of other compilers also have profilers. I'm just showing the one which I'm the most familiar with because, well, it's a Linux software. GCC can be called with the PG command, which will then instrumentize your executable. So when it's run, it will generate a data set that you can then use gprof to make a nice text report. And there are also other tools such as gprof2dot, which can help you generate dot diagrams. Last but not least, I should also mention that there are commercial tools which might help you for this kind of endeavor. The most widely known commercial tool for that is the Intel Parallel Studio, which is vendor specific. So it's done by Intel for the using for Intel servers. It also has a lot of other tools beyond a profiler, but the interesting thing is that it's free access for academics, so it's probably already deployed on your HPC clusters, and Intel is offering free training programs for that. Sorry. So, demo time again. What's going to be the most complicated thing? So, because the data set is quite large, I've already run Valgrind in advance, and I'm going to simply to show you the different steps of optimization I managed to do. Sorry. These optimizations are currently available on the alcoholic branch of Shura. First look at the situation at the beginning. Wow. So if you look at it, this is the type of information that we can have out of CacheGrind. You see all the different functions, the number of times they were called, and so on. You can see different type of reports. You can see the color of a function, which is the one that I have currently open, and you can see where the allocation is happening most of the time. There are two different pieces of code where it is happening. And we can see that, for example, it's called a lot in one of our functions. It's also called a lot in one of the mathematical function used in Shura. So the first thing that you can then try to do is try to remove some of the allocation which were happening once per loop, and try to move them outside of the main loop and having just the space reserved for your functions. So you manage this way to diminish some of the call to malloc. So keeping well, the point is that by successfully running optimization on each time, doing some tests, trying sorry, my fault. We can progressively manage each time to pinpoint where most of the allocation is happening. For example, one of the things which persists is that our scientific library is building tables to generate the random numbers on each time we do a draw, but we do one single draw per base in our sequences. So by avoiding building these tables, eventually we reach a situation where from several 100 million calls to malloc, we managed to get it down to 8 million. So a strong diminution of our calls. Another type of optimization. If we open this optimization, we can see that a big amount of time is spent computing logs, which makes sense because so we spend a lot of calls into log, which makes perfectly sense because of the statistical method is computed into log space. But we can observe something is that currently we're using the GNU scientific library to actually compute the logs. And for that, for every single computation, it means that each time we call into the library, which will then call a different internal function, which will then finally call the libc function, which will then finally compute the log. So for every single log which is computed as part of a statistical method, due to the library that we're using 4 calls into, four deep stack shifts to manage the computation just for every single one of them, because we're using an external library which is compiled this way. By moving to the standard C library, we now see that our calls are directly made from the part where the logs are computed. For every single one, we manage to avoid calling 4 different functions each time. So thanks to these steps, sorry, now I need to close everything. That's okay, that I can close. So by looking each time where most of the calls happens, progressively eliminating them or moving them outside of the loops or using pre-allocated memory or using a different library, so the actual calls to log can be inlined instead of having 4 levels of function calls. We eventually managed to divide by 2 the time it takes to compute one data set. And given that the sampler is the most time-consuming part of Shora, we managed to have some concrete results on the execution time. So that's it for the presentation. And with this, I want to thank you all for your attention. I also thank all the people around me. So that's my professor, Nico Berenwinkel. That's the past PhD who are developing the software on which I worked. That's the other developer currently working in our group with whom we've through a few interesting ideas, and all the past PhD and postdocs with whom we managed to make even more fun debugging situations. And also thank you for the organizer of this presentation.